remember what resistance mean in an electric circuit. Before getting into this, let us recall the Ohm's law and state the dependence of current, voltage and resistance. At constant temperature, the current flowing through the conductor is directly proportional to the voltage across it. Ohm's law states that V is directly proportional to the current I. Or we can say that V is equal to I times R or V is equal to R times I, where R is a constant of proportionality or the resistance of the conductor. We can state resistance as something that controls the flow of current. If a circuit has high resistance, its current reading will be lower. If it's lower, the current through the circuit increases. We can say that it is inversely proportional to current. What are the factors on which the resistance of a conductor depends? The resistance R not only depends on the material of the conductor but also on the dimensions of the conductor. We can see that the resistance R is directly proportional to the length of the conductor. More the length of the wire, more will be the resistance. Also, the resistance of the conductor is inversely proportional to the area of cross-section of that conductor. This means that the resistance is directly proportional to the length by area. We introduce a constant ρ called resistivity. This is the electric resistivity of the material of the conductor. We also learned that as the nature of the material changes, the resistance also changes. This is because as the nature of the material changes, the electric resistivity of the material changes accordingly. The constant of proportionality ρ depends on the material of the conductor as well as temperature, but not on its dimension. That is, resistivity does not change if we try to decrease or increase the length and area of cross-section of the material. Based on the resistivity, the materials are classified as conductors, semiconductors and insulators. The conductors have a minimum resistivity. Metals have low resistivities and it is in the range of 10 to the power minus 8 ohm meter to 10 to the power minus 6 ohm meter. Insulators like ceramic, rubber and plastics have resistivities 10 to the power 18 times or greater than metals or more. We have semiconductors in between them. They, however, have resistivities characteristically decreasing with a rise in temperature. The resistivities of semiconductors can be decreased by adding small amount of suitable impurities. Also, for a perfect conductor, the resistivity has to be 0, or for a perfect insulator, the resistivity has to be infinite. Resistivities of some materials are listed here in the table. You can see that the listed conductors, silver, copper, aluminium and mercury have resistivities in the range of 10 to the power minus 8 ohm meter. The insulators include pure water, glass and NaCl with very high resistivity values. The semiconductors such as carbon, germanium and silicon are having a moderate resistivity value compared to the conductors and insulators. Let us now study about the commercially produced resistors for domestic use and in laboratories. These are of two types, that is the wire-bound resistors and the carbon resistors. The wire-bound resistors are made by winding the wires of an alloy, say manganese, constantine, nichrome or similar ones. The choice of these materials is dictated mostly by the fact that their resistivities are relatively insensitive to temperature. These resistances are typically in the range of a fraction of an ohm to a few hundred ohms. Resistors in the higher range are made mostly from carbon. The carbon resistors are compact, inexpensive and thus find extensive use in electronic circuits. These resistors are small in size and hence their values are given using a color code. Some applications and uses of resistor include the circuit functions, dividing voltage, heating, LEDs and transistor. These resistors have a set of coaxial colored rings on them, whose significance are listed in the table. Their resistance is indicated by using electronic color codes. Different color bands or rings are marked on these resistors for different values of resistance. It usually consists of 4 bands. The first band indicates the first significant figure and the second band from the end indicates the second significant figure of the resistance in ohms. The third band corresponds to the decimal multiplier or the power to 10. The last band stands for the tolerance or the possible variation in percentage about the indicated values. Sometimes this last band is absent and that indicates a tolerance of 20%. For example, in this figure, the resistance has the bands red, red, red and silver. From the table we already discussed, the first 2 bands will give the value 22 and the third band gives the power of 10. The silver line here indicates a tolerance of 10%. Therefore, the resistance value is 22 into 10 to the power 2 ohms with a tolerance of 10%. Consider another example with 4 bands as yellow, violet, brown and gold. The resistance value here will be 47 times 10 to the power 1 ohm with a tolerance value of 5%. As we mentioned earlier, the resistivity of a material depends on the nature of the material and temperature. We study the dependence of resistivity on temperature in the coming sessions. Let us summarize what we have learned.
Manorama Horizon. Learning made simple.